Hello, welcome to Free Math. Let's take a look at the third problem from RMO 2016. For any natural number n expressed in base 10, let S of n denote the sum of all digits of n. For example, if n is 35, then S of n would be the sum of the digits of n, which is 3 plus 5 equal to 8. Yeah? So that is what S of n means. Now, we're going to have to find out all natural numbers n such that this holds. So this is what the problem is asking for. You have to find out all such natural numbers n which will satisfy this. Now, if you take a closer look at the expression, you might find some perfect cubes. Here, this is a perfect cube. 8 is a perfect cube. 1 is a perfect cube. So let us bring all the perfect cube terms on one side. We get this. Now, if you take a closer look at this, we have 3 cubes. So this is of the format a cube plus b cube plus c cube. What do you think about the right hand side? So here a is n, b is negative 2 times s of n, c is negative 1. So don't you think this is actually 3abc? Yeah. So we can write it that way. So a cube plus b cube plus c cube is 3abc. Now when will a cube plus b cube plus c cube be indeed equal to 3abc? That is only possible if and only if a plus b plus c is equal to 0. So that means we must have n minus twice of s of n minus 1 equals 0. Beautiful. All right. So what does that mean? So that means we can rewrite this expression like this. We can send 1 of s of n to the other side. So we have n minus s of n equals s of n plus 1. All right. Now, why do we write it this way? Now, if you are familiar with the divisibility rules of 9, you might notice that this expression is actually divisible by 9. You can take a very simple example for any value of n. For example, if n is 91, let's say, then s of n would be 9 plus 1, 10. Then n minus s of n would be 81, which is divisible by 9. Yeah. So the number n need not be divisible by 9, but n minus s of n will always be divisible by 9. So let me just clear everything on the screen. All right. So n minus s of n is divisible by 9, which implies that Sn plus 1 would also be divisible by 9. All right. So we're going to make use of this fact to prove, to find out the values of n satisfying this. Okay, one more thing. From this equation, n minus 2 twice of Sn minus 1, we can rearrange and we can get that n is in fact equal to twice of the sum of its digits plus 1. So we have two important facts on the screen right now. We're going to make use of these two. Which two? So we know that 9 will divide s of n plus 1, and also the number that we are looking for is in fact equal to twice of the sum of its digits plus 1. Now you see, if the number is of this format, because sum of the digits of n will always be a very small number usually. Yeah. So and you're taking twice of it and then adding 1, so we can estimate that we can make a very logical claim that the number of digits in n cannot be more than 2. I mean, n cannot be a very big number. Okay, so we are making this claim that the number of digits in n cannot be more than 2. Now imagine, suppose n is a 3-digit number. Yeah. So the largest three-digit number that you can possibly think of is 999. So therefore, the sum of the digits would be at the most 27, right? At the most 27. So s of n will be less than or equal to 27. So that means twice of Sn plus 1 will be 2 times 27, which is 54 plus 155. So now recall that n is twice of Sn plus 1. So we can replace this with n. So we are basically getting n is less than 55, less than or equal to 55. But remember, we said that n is a 3-digit number. Now we are getting n to be a 2-digit number, which is a contradiction, right? So why did we get this contradiction? Because we imagined n to be more than 2 digits. Yeah. So this claim is in fact valid, the number of digits of n cannot be more than 2. Okay, so n has to be a 1-digit number or a 2-digit number, right? So that means S of n can at the most be 18, because maximum, the highest, biggest 2-digit number is 99. So the sum could at the most be 9 plus 9, which is 18. Fine. So now recall that 9 divides Sn plus 1. We saw that in the previous slide. The 9 will always divide Sn plus 1. Now since Sn can at the most be 18, that means Sn can take either 8 or 17, because 8 plus 1 is 9 and 17 plus 1 is 18. So Sn can take only two values, which is 8 or 17. So that means n can be either 17 or n can be 35. These are the only values of n which will satisfy Sn equals 8 or Sn equals 17. Now, now remember, we have to satisfy this condition as well. N equals twice of Sn plus 1. Now, if n is equal to 17, let's check. 2 into S of n will be, so if n is equal to 17, then we have S of n is equal to 8. So twice of Sn plus 1 will be twice of 8 plus 1, 16 plus 1, which is 17. If n equals 35, let's check, then twice of Sn plus 1 will be twice of Sn will be 3 plus 5, 8 plus 1, which is 16 plus 1, which is 17. So n equals 35 cannot be true. Yeah. Yes, yeah, correct. So n equals 35 cannot be true, because here it is not satisfying, this condition, right? N equals 35 is not satisfying this condition. So at the end, we just have one solution, which is n equals 17, which is n equal to 17. Let me just clear everything off the board. N equals 17. So the only solution is n equal to 17. Now we can in fact verify this. 17 cubed is 4,913. You can just plug in the values and check. Turns out it is also 4,913. So the only solution to this problem is n equals 17. Okay, so thank you for watching. If you have any doubts, please let me know in the comments. Thank you.